Hello my friends, welcome back to another exciting day of AP Calculus. Today we're going to be looking at the definite integral, defining what that means, as well as one additional approximation method known as trapezoidal approximation. Before, the area under the curve, we were looking at how do we connect from like velocity, time, and going to distance. Turns out that if we have the area under the curve of a rate, thinking about in terms of time, that can give us the accumulated value, the total value that we get. We had this summation statement, this rectangular approximation method using the summation statement here, where we see that the sum, which was that sigma notation, we have starting at the first rectangle. So I equals 1. I represents the number of the rectangles. We're going from I equals 1, the first rectangle, up to the nth rectangle. Now, if we have 6 rectangles, it's going to be 6. If we have 17 rectangles, it's going to be 17. Thinking about a rectangle, every rectangle is base times height. The delta x, that's going to be the base of one of our rectangles. And I can see that down in the diagrams that I have below. So let's write that. That delta x is going to be b minus a over n, where our interval is a b, and we have n many intervals. So it's taking that entire region and dividing it into n many partitions. Now that's if we have a fixed curve, or if we're going to have every delta x, every rectangle equally have the same base, have the same width there. That's not always the case. But we've got base, we've got the height. That's the height of our rectangle, which is going to be the height of the function, the value of the function evaluated at our x sub I. Now, the three approximations that we've had so far, just to recap, we have left rectangular approximation, or RRAM, we have a midpoint rectangular approximation, or MRAM, and we have the right rectangular approximation, or RRAM. So I've got the same curve shown 3 times here, each demonstrating how we figure out the L, the R, or the M for our rectangular approximation. When we have an interval, an LRAM is going to start from the left side of the interval. So the height is going to be selected from the left side of the interval. No matter where it is, it's from the left side over for the interval. The midpoint approximation, so here I might have my interval going from 1 to 1.5, we're going to take the height at the middle of that interval. So it's the middle of the rectangle is going to hit the curve. We can see that again there. And thirdly, our right rectangular. When we have our interval, our rectangle is going to start on the right side of our interval. So all of our rectangles are going to come from the right, whereas for the left, all of our rectangles come from the left. Now, we saw before that those x values, those are the values that we are using for the height of our rectangles. Now, our left approximation is going to be using the left endpoints. For the midpoint, we're going to start off A. A is always our starting value, and we're going to have I minus 1/2. That shifts that delta x, so we're taking the x value from the midpoints of all of those intervals. And lastly, we're going to have A plus I delta x for our right rectangular approximations, and that takes it, so A plus delta x would say, putting it at the right side of the rectangle. So that's just how we determine what the x values are for our intervals. Now, if we look at these 3 graphs, sometimes we've got an overestimate or an overapproximation, sometimes we have an underestimate, an underapproximation. Let's think about what makes, or how we can decide each case. LRAM, we've got our left rectangular approximations. An underestimate, if we look at our curve, when is LRAM an underestimate? So when are our rectangles below the curve? Well, that's here, that's here, that's here, and that's here. What's consistent about our curve on those parts? Well, our curve is increasing at those points. So LRAM is an underestimate when our function is increasing. We can get rid of decreasing. So make a note to yourself, draw that in. And the opposite is going to be true for an overestimate. We can see on our curve that when our function is decreasing, all of our left approximations are going to be greater. So we have an overestimate when our function is decreasing, and we can see how that's the opposite. So that's our left rectangular. You can figure out what's going to happen for the right. Fill that in for yourself. Now today we're going to have a new type of approximation. And you go, well, left is always partly over, partly under. There's always going to be like this triangular what's going on there? We're always going to have like this triangular region that's missing or counted extra when we have a left or right approximation. What if we combine those two? What if we turn that into that extra triangular region in each case? So if we have that extra triangular region, that's going to be called a trapezoidal approximation. And that's what I have down at the bottom of this page of notes. So our new trapezoidal approximation is going to be the average of the left and the right approximation methods. So that's going to be, I'm going to make a note down at the bottom, it is going to be 1/2 LRAM plus RRAM. So if I can find my left rectangular approximation, if I can find my right rectangular approximation, trapezoid is going to be the midpoint. And I can see, I'm going to zoom in on my graph right here. Here's our box for our left rectangular approximation. Here's our approximation, our rectangle for the right rectangular approximation. And the trapezoid cuts that section in half along the diagonal. So that's how we have the average. And you can see it's probably going to be a little bit of a better approximation. Back. Now, thinking just what we talked about with the LRAM and RRAM, when are we an underestimate and when are we an overestimate? Let's take a look at the curve that we have there on the left. When is the trapezoidal approximation an underestimate? So when are we below the curve? That's this section. Ooh, and it continues. So it's not just increasing. It's partly increasing. It's partly decreasing. So this section's an underestimate. So it's really just this section is our underestimate. How is that different from this part? So we have the increasing, decreasing. So that's not it this time. We see that's where we change concavity. We are an underestimate if our function is concave down. The things I think calculus always makes sense. Draw it out, look at it. On the opposite, trapezoidal approximation is an overestimate when our function is concave up. So we have these 4 different approximation methods: left rectangular, midpoint rectangular, right rectangular, and trapezoidal approximation. That is just the average of the left and the right. These are just approximations. How can we get the true area under the curve? How can we take this and make this so fine that we know it's the exact area? Well, if we have 10 rectangles, if we have 100 rectangles, well, what if we keep on increasing that? So what we have is going to be called the definite integral. So our rectangular approximation methods can be made more accurate by increasing the number of rectangles. The area under the curve then, on an interval AB, can be determined as then, how much do we increase without bound? So we're going to say, we're going to increase that without bound. And I'm going to define this as going to be the limit as n approaches infinity of the sum starting at 1 to n. So there's our n. It's going to be increasing towards infinity. How do you add together an infinite number of rectangles? Of f of xi delta x. And once again, our delta x is b minus a over n. And here our xi does not matter. It can be anything, because if you think about it, as we have an infinite number of rectangles, the left and the right sides are essentially the same thing. This is what we're going to call a definite integral, or a Riemann sum. So the definite integral of f, what we say the definite integral, is given by the limit, once again, as n approaches infinity of the sum from I equals 1 to n f of xi delta x. Now, rather than writing all of that, we have a more elegant expression. And maybe you've seen this before. I'm going to use this symbol, and that's the German long S. Put my lower bound at the bottom, my upper bound at the top, f of x dx. Getting back to our differential notation, f of x dx. And you can see the parallels here. We've got our function f of x. We have the width of our rectangle, delta x, back to dx. So what this statement is called is the integral. This is called the integrand. The function is our integrand, and this is the integral symbol. This means the area under the curve, f of x dx, f of x, starting at a and going to b. So we have our lower bound of integration, we have our upper bound of integration. So that's the left side of our area, the right side of our area, and we are integrating, or finding the area with respect to x. So I would read this as the integral from a to b of f of x dx. That's what we're going to define as the area under the curve. Now, if f of x is non-negative, meaning it's positive above the x-axis, and integrable, meaning we have a limit that exists, and we can find the integral, over a closed interval ab, then the area under the curve of y equals f of x from f a to b is the integral of f, or, just to rewrite this, is the integral from a to b f of x dx. Let's take a look. Put this and use this notation. First one, I want to take this function, x cubed plus x sine x, on the bounds 0 to pi. I want to first rewrite the area under this curve using my limit and summation notation. That would give us the limit as n approaches infinity of the sum of I equals 1 to n. Now our function is x cubed plus x sine x, hold that open, sine of x. We're going to take the sum of that multiplied by delta x. So I put those placeholders in there because our x is going to be that a plus I delta x. In this case, our delta x is b minus a over n. That's going to be pi minus 0 over n. That's going to be pi over 0. So our x value that we're going to be substituting is going to be 0 plus pi over n times I. I'm going to rewrite that now. I've got pi over n I. That's going to be everywhere where there's an x, I have a pi over n times I. And lastly, sine of pi over n times I. Wow, look at all that. Instead, using our integral notation that we just have right there, our area is going to be the integral, using the integral symbol, from a, 0, to b, pi, of our function, x cubed plus x sine x. I'm going to close that, group that in parentheses, and my variable of integration is dx. So much nicer. Let's take a look at two examples where we're actually going to be evaluating integrals, but we're going to be interpreting them in terms of an area. So we're going to think about what this is geometrically. First one, we have the integral from 0 to 3 of x minus 1 dx. Let's graph that. X minus 1, that's just a line. We've got a y-intercept of -1, we have a slope of 1, we have an x-intercept of 1, and we're going up to 3. So the highest point on that graph is going to be the coordinate 3, 2. I want to find this area, so all of that space. And you go, wow, that simple thing looks crazy. No, it's area. First off, what I notice is that we have some parts that is below the x-axis. Where did that go? We have some parts that's below the x-axis. That's going to be negative. And if we think about velocity, if our velocity is negative, we are losing displacement. We're moving to the left. I'm going to visualize this being as two triangles. That area is -1/2. And then the area on the right, we've got a base of 2 and a height of 2. That's 4 divided by 2 is 2. So our total area here is 3/2. That's it. It's the area of a triangle. We got this. Then you look at the next one. The integral from 0 to 1 of the square root of 1 minus x squared. Yikes. Well, let's pause and think about it. If you were to graph that, you'd see that's a quarter circle from 0 to 1. Well, that's a quarter circle. We have a radius of 1. Well, and since the integral tells us the area, pi r squared over 4, because it's a quarter of a circle, we get pi over 4. That's all we got to do. It's find the area under the curve, starting at the lower bound, going to the upper bound. You're going to try some stuff out. Good luck. See you next time.